Hello everybody, this is Mr. Lockett. This is the Law of the Conservation of Energy notes, and I'll be taking you through it today. Make sure that you have a journal out and a pencil or pen, something to write with, so you can get the notes down. Feel free at any time to pause the video if I'm moving too quickly for you to write. I want to start with the Law of Conservation of Energy. What the law says is the total amount of energy in a system is going to remain constant. So therefore, you can never destroy or create energy. You can simply convert it from one type of energy to another. Give you a couple examples here. Example number one is going to be a ball. If I hold a ball above the ground, initially the ball doesn't have any kinetic energy. It's not moving. But what it does have is potential energy. It has potential energy because we know, based on what we've done in class, that mass times the acceleration due to gravity times the height is going to give us our potential energy. So in this case, we have a ball that has some mass. We know the acceleration due to gravity is 9.8 meters per second squared. And we know that it has some height above relative to the ground. So it has potential energy. Well, once I drop the ball, the potential energy is going to be converted into kinetic energy. So the initial potential energy is all going to be converted into kinetic energy, the energy of motion. And therefore, the conservation of energy. Energy is conserved. Example number two, we've been looking at a pendulum in class. So if I'm holding this pendulum, it's not moving, it has a kinetic energy equal to 0. No motion, can't have any kinetic energy. Well, but it does have potential energy, right? Because it could do motion. As soon as I let it go, it'll start to move, so it has some potential energy. So it's going to be greater than 0. Well, once I release it, all of that potential energy is going to be converted into kinetic energy. And about the point where right in the middle of its swing, the kinetic energy is going to be its greatest, it's going to be the highest, and it's going to be 0 potential energy. Well, if it continues this swing, it's going to go back up the other side to the top of where it's not moving again, and the potential energy will be greater than 0, and the kinetic energy will be 0 because it's not moving. So the potential energy at the beginning is going to equal the potential energy at the end of its swing, assuming that there's no friction. So this is going to be the case for a situation not that we can do in class. Because we know that based on what we've seen in class is that it will eventually slow down, the pendulum will stop. And that's due to a couple examples of friction that we see. One of them is air resistance. So we see that the ball has air resistance because of molecules in the air, and therefore is going to run into some friction, causing friction, it's going to slow down. The other is, the pendulum has to be swinging from something. So the friction, we wrap some string around a bar, so the friction caused by the rope or the string rubbing on that bar is actually going to create some friction that's going to cause it to slow down. So if there was no friction in a frictionless system, the pendulum should actually continue to swing back and forth and back and forth and back and forth. But we see that it slows down because there is this friction. So you could talk about a pendulum in a frictionless situation or a situation where there is friction. And if there was no friction, the potential energy at the beginning, back when we were here, should equal the potential energy at the end of its swing when it's here, right? This is all because of the conservation of energy. Example number 3 is a car. So if you're driving along in a car and you slam on the brakes, you're going to start slowing down. So you have all of this initial kinetic energy, and as soon as you slam on the brakes, you slow down, you're losing some of that kinetic energy, but where is that kinetic energy going? Well, the kinetic energy is actually being transferred to the ground through the friction with the tires, some of it, and a lot of it's being converted into heat. Once you slam on your brakes, those brake pads are going to heat up really fast and get really warm in your car. So the kinetic energy of motion is being converted to heat energy. Example number 4 is a light bulb. This is a little bit of an extension of the last one. How is it that you can add 100 joules of electrical energy to a light bulb, but you only get 70 joules of light energy out? Go ahead and take a guess real quick. Where is the other 30 joules going? It's going to heat energy, that's right. Hopefully you got heat energy. That light bulb's really warm. If you ever touched a light bulb that's been on for a while, it's pretty hot. So you're putting in electrical energy through the socket that you plugged it into, and then it's giving you some light energy, and then also some heat energy. So you've got a conservation of energy, the 70 joules of light energy plus the 30 joules of heat energy to to give you the 100 joules of energy that you started with, and the conservation of energy is once again shown. That's it for today. Hopefully you got all these notes down, and I'll see you in class.